In this video, we're going to code the merge sort sorting algorithm in Java. In my bubble sort video, I got a comment that said, "Can you do merge sort next? Ask and you shall receive." Now we know this sorting algorithm is going to be faster. It has a complexity of big O of n log n, but how much faster does it actually work out to with a real implementation? With bubble sort, we got up to sorting 1,000,000 numbers, but it still took about 37 minutes. With merge sort, of course, we're going to see how much faster we can do 1,000,000 integers, but we're even going to take it a step further and go to 10 million, 100 million, even a billion if we can get there. If this is your first time watching this channel, my name is John, and I do a new Java tutorial video like this one every single week. So be sure to leave a like and hit the subscribe button so you don't miss the new video every week. And as always, you can get the full source code of this program in the link down in the description, so go and get it. As with all of the sorting algorithm videos so far, I start with a little bit of a program setup. First, I create this array of ints called numbers. Here we're just starting with a length of 10, so we'll have 10 numbers to sort. And then we loop through that array to fill it with random ints essentially between 0 and 1,000,000. So that gives us our unsorted array that we want to sort. And then after that, we print out the before state, the unordered array. And then we have the call to our merge sort method, which is currently empty. That is what we will be writing in this video. And then after that merge sort method is called, we should have a sorted list. And so we just print that array again, and we should see it in perfectly sorted order. I know we want to just dive headfirst into the code, but before we do, it's a good idea to get a mental model of how merge sort works. This is a diagram just from the merge sort Wikipedia page that gives a pretty good picture of how it works. You start out with your unordered array. You divide that array into two halves and merge sort each half recursively. And then once each half of your array is sorted, so this half is in order and this half is in order, then you go through a process of merging both of those halves of your array into one array again, and that one array will be in order. How that merge process actually works is key, and we'll get into that more when we get to the code. We start with this completely unordered array, and we divide it in half into two arrays. And then we tell each array to merge sort itself. That's the recursive part of this algorithm. So you can see here, this first array is being split into two halves, and then the same merge sort algorithm will be called for each of these halves. Well, the first part of the algorithm is to again split into two halves and merge sort each half. So here you can see each half being divided again into two halves. Then here in the third level of this example, we still recursively merge sort each of these very small arrays. And again, the first step to doing that is dividing them. So eventually that gets us down to where we have a one element array for each number in the array that we started with. So this is the whole dividing portion of the divide and conquer of this algorithm. We divide into smaller and smaller problems until we get to where all of our arrays just have one element in them. And we know that an array with just one element in it, it's already in order. It can't be out of order. There's only one element in it. So once we get to that state, we start the conquer portion of our divide and conquer algorithm, and that is the merging. Let's take a look at this example merge here. So to start with, we know that we are merging two arrays that are already sorted. We know that each one is in order with itself. So here we have 27 and 38 and 3 and 43. Each of those are in order with themselves. What we do is we start by comparing the first element of each array, which here is 27 and 3. And we say which one is smaller. And here, 3 is smaller. We take the one that is smaller and add it to our merged array. So here we add 3 as the first element in our merged array. And then since we added 3 to our array, we move over and look at 43. For our other array, since we haven't added 27 yet, we're still comparing 27 with that next element of the other array. So the next step, it would be comparing 27 to 43. Which one of those is smaller? It's 27. So we go ahead and add 27 to our merged array. And then since we added 27, we move over to look at 38. So we're comparing 38 to 43. Which one is smaller? 38. So we go and add that to our merged array. So then when we add 38, we now have no elements left in this array that haven't already been added to the merged array. When that happens, we'll go through all the elements in our other array that still has values yet to be added, and just add them all in order. In this case, all we would have left is 43, so we would just add 43 to our merged array. So after that has happened, our result is one merged array that has all the elements of the two arrays we were merging, all in perfect order. For a while, what got me is, how do we know that doing the comparisons and the adding in that way, how does that result in a perfectly ordered merged array? Well, the key is that both of the arrays that we're merging are already in order. If neither of these two arrays were in order, merging them with the algorithm we just talked about wouldn't work right. We're looping through both of these arrays from their lowest values to their largest, adding the lowest value that we find to our merged array. and then we slowly progress to higher and higher numbers in each of these arrays, and keep adding the next lowest one that we find along the way. Each of these merge steps that we see operate exactly the same way. And then this final merge down at the bottom looks more complicated, but it's really not. We do the exact same thing. So now that we've gone through all that, let's get to the code. So again, all the magic in our code is going to be happening in this merge sort method. The first thing we want to do here is to create a variable for the length of this input array, because we're going to need the length of this input array many times throughout this algorithm. So having a variable for it just makes our life a little easier. So we'll call it input length and set it equal to input array dot length. So remember, we are going to be calling this merge sort method recursively, which means, yes, we're going to be starting it by calling it on one larger array, but even as it gets further and further down into these sorts of levels here, where there's only one or two elements in each array, we're going to be calling that merge sort method recursively on smaller and smaller arrays until we're eventually calling it on arrays with just one element in them. And we know that arrays with just one element are, of course, already sorted. So actually, the first thing we want to do is check that if the input length is less than 2, which of course means we either have an empty array or an array with just one thing in it, then we just return. So that accounts for like this part of the algorithm here, where we have a bunch of arrays with just one element in them. We don't divide that into two arrays and have each side sort itself. We only have one element in it. So we already know it's sorted. So this accounts for that. If the array that comes in is less than 2 elements long, which is essentially either a 0 or a 1 element array, then we just return. There's nothing for us to do, it's already sorted. But if that's not the case, if we have 2 or more elements in the array that we're looking to sort right now, then we continue. The next thing to do in our algorithm is to divide our array into 2 arrays. To do that, we need to get the midpoint of our array, which is just half of the input length. So if we came in with an input array that was 10 elements long, we want to divide it into 2 arrays, split at that 5th element in the midpoint. So to do that, we'll create another variable. We'll call it mid-index and set it equal to the input length divided by 2. And then we'll actually create our 2 arrays for the left and right half. We'll create an int array, call it left half, and set it equal to a new int array that we will create. And we need to give it a length, and we can just use mid-index, because we know that'll give it half the length of our original array. So again, if our input array was 10 elements long, this mid-index would be 5, and our left half array here would have a length of 5, which is what we want. Now we have to create our right half equals new int array, and we also need a length here. And to do that, we're actually going to use input length minus mid-index. You might be thinking, hey, we can just use mid-index here also. But that ends up not working right for arrays with odd numbers of elements in them. So if this input array came in with 9 elements in it, then input length divided by 2 would actually end up being 4. So the left half would be 4 elements long, and we need to hold the other 5 elements in the right half. So input length minus mid-index works great for that. That would be 9 minus 4, which gives us the 5 elements that we need. So now we've created these 2 arrays, left half and right half, but they don't have any elements in them yet. So we actually have to populate them with all the elements from our original larger input array. So first we'll fill up the left half by doing for int I equals 0, I less than. So what do we want to use here? We're just trying to fill up the left half array, so we can only loop until the end of that array. So what we actually want to use is this mid-index. And then of course, increment I plus plus. So we're looping from 0 to the length of our left half. So this I is what we'll be using as the index of our array. And what we want to do here is copy the elements from our original input array into our left half array. So to do that, we just set left half at I, the ith index of our left half array, to be equal to the input array's ith element. So after this for loop completes, our left half array will contain all the elements from the left half of our input array. And now we want to fill up the right half array with all of the elements of the right half of our input array. So it'll be similar, but not exactly the same. We can copy paste here as a start. Here we actually want to start with I at the mid index and loop until I reaches the original input length of our input array. And of course, still increment I each time. So essentially what we're needing to do is loop through the second half of our original input array. And that's what this allows us to do here. So we start at that mid index at the midpoint and go until the end, this input length. And we still want to use input array I here, but now using I as the index of this left half that we're assigning to doesn't really work. Again, if we have a mid index of 5, we don't want to be starting by setting the 5th element of our left half. We want to start at the 0th element. But we still do want to use I here because we do want to be starting at the midpoint of this original input array. What we want to modify here is instead of setting left half I, we want to set left half of I minus mid index. So again, for example, if we have a mid index of 5, this will start with 5 minus 5, which will be 0, the 0th index, which is what we want. And then when it moves on to the next one, then I will be 6, and we'll be setting the element at 6 minus 5, which will be 1, the next element in the array. Oh, and of course, also we want to change this to right half instead of left half. We don't want to be overriding the left half again. We want to be creating the right half. Essentially what is happening here is we're filling up the right half array that we created with all the elements from the right half of our original input array. Okay, now after all of that is completed, we have our left half and right half arrays that contain the left half and right half of our original input array. What does our algorithm say has to happen next? Well, what we do is we merge sort each of those two arrays, and then later we'll merge them together. So how do we tell our algorithm to merge sort each half of our array? Well, that's actually the simplest part of this so far. We have a merge sort method that we're writing, so all we have to do is recursively call it with our left and right halves. So we will literally just say merge sort left half and merge sort right half. After this point in the finished algorithm, we should have two completely sorted halves. And the last remaining step would be to merge those halves together. So that's what we need to do here. We need to write the code to merge these two sorted arrays into one large sorted array. And to simplify our code a little bit, we're actually going to write a method to do that, just so we don't clutter up this merge sort method too much. So we'll create a private static void method called merge. Now it needs to take in actually three things. It needs to take in the int array, the original combined input array, so it can merge the left and right arrays into it in sorted order, and the left and right half arrays. So int array left half and int array right half. Similar to how we did in the merge sort method, first we actually need the length of our left half and right half. So we can do that the same way. Int, we'll call it left size equals left half dot length, and int right size equals right half dot length. Next is the part of the algorithm that can probably be the most confusing. This is where we're going to be looping through the elements in our left and right arrays, of course from lowest to highest because they're already in sorted order, comparing the first elements of each and adding the lower one to our merged array, and keep comparing the lowest element of each array and adding the lower one to our merged array until we run out of elements in our left and right arrays. So we actually need three iterator variables, one for walking through the left half array, one for walking through the right half array, and one for walking through our merged array. So to do that, we'll need three ints that start at 0. So we'll need int I equals 0, int j equals 0, and int k equals 0. Now, if you want to be cool, you can put all these in one line and just separate them by commas. If they're all the same data types, you can do this. So you can just have int I equals 0, j equals 0, k equals 0, and put all those in one line and look really cool. I will be the iterator for our left half, j will be the iterator for our right half, and k will be the iterator for our merged array. We'll actually use a while loop here, and we're going to loop while I is less than left size and j is less than right size. So this is basically looping until we run out of elements in the left array or we run out of elements on the right array. So here what we actually want to do is compare the ith element of the left half with the jth element of the right half. So we're saying here if left half at I is less than or equal to the right half at j, then this is the smaller of the two numbers, or they could be equal and it doesn't matter which one we add, so we'll just add the one in the left half array. We will add that element at left half I to our merged array. We know that is the lowest element that we are looking at so far. So we'll say input array at k, which remember is our iterator for our merged array, and set it equal to left half at I. So now that this ith element in our left half array has been added already to our input array, our merged array, we want to increment I to then look at the next element of the left half array. So to do that, we just say I++. Now otherwise else, so here we checked if our left half at I is less than or equal to the right half at j. And if this wasn't the case and it didn't enter this if, then we know that this jth element of the right half is actually the smaller of these two numbers. So in that case, we would add the jth element of our right half to our merged array. And so that looks very similar to our code above. We'll say input array at k, set that equal to right half at j. And then since we're adding the element that we found in the right half array, we need to increment j. So in the example here, what just happened is we've just compared the first element of our left and right half arrays. We've compared 3 with 9. In this case, 3 was less than 9. So we add 3 to our merged array. So here in our code, it's as if this element in our left half array was less than the value we were looking at in our right half array. This assignment is like adding 3 to our merged array. And then we increment I, which means we will shift from looking at this 3 to looking at this 27 and comparing it with the first element of the right array. If the first element of our right array happened to be smaller, then we would have added it to our combined array and incremented to look at the next element of the right array. And that's what this else is accounting for. Now, either way, no matter if we added the element from the left or the right array, either way, we want to increment our combined array iterator, which here is k. So completely outside of that if-else, we want to do k++. Now that we've set this first value, we next want to set the second value. So now this will keep looping through, going through the arrays at each half and adding the lower element to our merged array until this condition is met, which will go until we either run out of elements in our left array or run out of elements in our right array. Either way, there's nothing left to compare. But if we ran out of elements in either our left or right array, we still have some numbers left in whichever array we didn't reach the end of. And so after this while loop, essentially we just need to do cleanup and add all of the elements that are still remaining in either the left or right array. So using the smaller merge as an example, first we start by comparing 27 and 3. 3 is lower, so we add it. And then we're comparing 27 to 43. 27 is lower, so we add it. And then we move to comparing 38 with 43. 38 is lower, so we add it. At that point, we have added all the elements in this left array, and there's nothing left. So that would trigger this to exit the while loop. But we still haven't added the rest of the elements from our right array. And so we just need to loop through those remaining elements and add them to our merged list. And in this point in the code, it could be the left or the right arrays that have elements left over, so we can just have code for both of them. So to account for any possible elements left over in the left array, we can say while I less than left size, input array at k equals left half at I. And then we want to increment the iterators of both I and k. So how this works is if we already ran out of elements in our left array, it would just bypass this completely. And then we do the same for any remaining elements in our right array, but just with different variables. So we would say while j is less than right size, then input array at k equals left half at j, and we do j++ instead of I++. So at that point, we've looped through each of our two halves, constantly adding the lower of the two values to our merged array. We loop through and add any remaining elements to the end of our combined array. So now by the end of this merge method, this input array will have all of the elements from the left and right half arrays combined in perfect order. So now all that's left to do, we've created our merge method, we just haven't called it yet. So here, let's get rid of this and actually call our merge method with our left and right half arrays. So what we have to give it is our original input array, as we have here, and then our left half and right half. Left half, right half. Okay, I think that completes the algorithm. Let's zoom out a little bit to have a look at our handiwork. But before we get too excited, let's actually run it and make sure it works. So here we'll do it with an array of just 10 elements. Let's give it a try. I don't know, we actually got an array index out of bounds exception. So there's some problem somewhere where we're trying to reference an index of an array that doesn't exist. So we're trying to access like the fifth element of an array that only has 4. So let's click this line so we can see exactly where it's happening. I see the problem, it's a copy paste error. I'm still using left half here when I should be using right half. Okay, so that's an easy fix. Let's go ahead and run it again. Okay, so we can see the before state here. We started out with a completely unsorted list, and then after, it looks like this list is perfectly sorted. Hey, so far so good. That's looking great. Let's run it a few more times just to be sure. Looks good. Looks good. Looks good. Awesome. Okay, so now that we have the algorithm working, let's put it to the test. Right now we're only using 10 numbers. Let's crank it up. Let's do 10,000. Run that. So it did that in no time, less than a second. You couldn't even notice it. So let's crank it up again and do 100,000. Run that. Wow, again, pretty much instantaneous. You know, just 1 or 2 seconds. It probably took more time to actually print out the sorted list than it did to actually do the sorting. So if 100,000 is that fast, I don't see a reason not to keep going. Let's step it up to 1 million. There it goes, printing out the randomly sorted list. Oh, and it already is starting to print out the sorted list. And in that case, in like 7 seconds. And really, it looked like most of that time was just spent printing out the list themselves rather than actually doing the sorting. So let's start getting nuts. Let's do 10 million. Okay, it's printing out the unsorted list. So it hasn't even started trying to sort them yet. It has to go through all this printing before it even begins sorting. Let's see. You'll see it stop for a second in a moment when it does its sorting. Okay, it stopped, now it's sorting, and it's already done. And now it's printing out the list in sorted order. So this is the part that's taking a while, not the actual sorting. So I think what we'll do next is now that we know that it's sorting the arrays properly, we'll just comment out the actual printing of it so that we know that the amount of time that it takes is the amount of time that it actually took to sort the list and not just print it out. That took about a minute to run, but as you saw, most of that time was spent just printing out the lists. So let's go ahead and comment out both of our print array calls. So we're still creating the random array and we're still sorting it, but we're just not bothering to print it. So we can get a good feel for exactly how long the actual sorting is taking. And let's run it. Before, okay, and after. So we know when it printed out the word after, that meant it had already sorted the list. So we can see up here that took about 3 seconds to sort an array of 10 million ints. So of course that kicks the daylights out of the last 2 sorting algorithms we made. Of course it just wrecks BOGO sort, which took 5 hours for just 14 ints. But also it's worlds better than bubble sort, which took about 37 minutes to do 1 million. This did 10 million in just a few seconds. Okay, so it took 4 seconds to do 10 million. Let's keep going. Let's do 100 million. How long is it going to take? 4. Still sorting. This one is taking a little bit longer, but it's doing 100 million. After. So it's done. So it went from 11:35:19 to 11:35:43. So that is still less than 30 seconds. That's less than 30 seconds to sort 100 million ints. Not to mention actually creating this random list and all of that. But even setting that aside, sorting a list that large in less than 30 seconds is awesome. But hey, I don't see a reason not to keep going. Let's see if we can do 1 billion. What happens if we do 1 billion? And run. Duh. Oh, we ran out of memory. It looks like we can't, at least on my computer, we can't create an array of 1 billion ints and sort them. So at least on my computer, Java just doesn't have the amount of memory that it needs to do this sorting for 1 billion ints. So that's a little bit of a bummer. I would like to have seen how long it would take. But I mean, that's okay. That's a great problem to have. We can sort so many numbers that the limitation is to the memory that we have on our machine rather than the speed of the algorithm. So it looks like that's what an algorithm with big O of n log n complexity can do for you. If you enjoyed this video or learned something, please let me know by leaving a like. And if you'd like to see more Java videos like this one in the future, be sure to subscribe so you don't miss the new video every week. And really, thank you for taking the time to like and subscribe. It's the only way these videos get out to help more people, and so I really do appreciate it. And remember, you can grab the source in the link below, and so if you can run it on your computer and get it to work with 1 billion ints, I would love to hear about it. Thanks for watching.